Okay, good afternoon, everybody. My name is Rudy Shankar, and I am the director of the Energy Systems Engineering program at Lehigh University. And welcome to the fifth in our fall seminar series under Energy Systems. And it gives me great pleasure to introduce a dear colleague and friend, REVIS James, who's going to talk about a subject matter that he has really burnished his credentials on, energy technology and policy. He's worked for many years in this area while at EPRI, and I would say he was one of the pioneers in developing some of the strategies that we're going forward with. Electric power in the U.S. is, it's a complex network of generation and delivery technologies, and there are many stakeholders. The public is a big stakeholder, and in some ways, energy is treated like a civil right. And so you can see there are lots of inputs that go into what the grid ought to look like. But today we're driven by a much larger driver, which is climate change. And we have to make changes in the way we generate energy, the way we use it in energy, and what goes along with it are some of the policies that dictate how the business is run. And REVIS James is the ideal candidate to talk about this. And I just want to mention to my students that we'll have expansion of what REVIS will be offering today in 2 lectures next semester. So this is like a preview of what you'll be hearing next semester. So a little bit about REVIS. He was the Vice President of Policy Planning and Development at NEI, responsible for development of policy positions affecting nuclear power. This scope included electricity market issues, used nuclear fuel, development of advanced nuclear power technologies, as well as financing and tax issues. He was responsible for managing NEI's relationship with key external stakeholder organizations and the financial community. Formerly, REVIS spent 23 years at the Electric Power Research Institute, leading development of research strategy and several technology research programs. As director of the Energy Technology Assessment Center, he focused on strategic priorities for the electric power industry. Prior to that, he led EPRI's long-term technology innovation program for several years. He also directed research programs for coal and gas generation, instrumentation and controls, human performance, and maintenance program optimization. REVIS spent 2.5 years in Paris, France, leading a joint strategic research and development program between EPRI and Electricité de France. And he worked previously at Bechtel, Aaron Engineering Research, and Impel Corporation. REVIS has a Bachelor of Science degree in nuclear engineering and electrical engineering and computer science, as well as a Master of Science degree in nuclear engineering, all from the University of California at Berkeley. Welcome, REVIS.
Thank you, Ramesh. Appreciate that. I'll just make a few brief remarks, and then I'm going to put up a presentation I'd like to use during our talk today. As Ramesh said, I'd like to talk about the relationship or intersection between policy and the energy electric power sector, specifically not energy, but electric power. And the thing I would like to start with is just to recognize that electricity, as Ramesh said, is an essential infrastructure now. It's not really in any sense optional, and therefore there is a new level of expectation with respect to cost, reliability, and other environmental impact associated with electric power. So what I want to focus on today is understanding the relationship between the many different stakeholders, because my objective here is to communicate with you as students, researchers, people that will be working in the industry in the future, to recognize how important it is to structure, conceptualize, communicate your work in a way that's accessible to policymakers. Because the effectiveness of the technical work that we do is vastly diminished if that aspect is neglected. Simple as that sounds, it has a lot of nuances to it. So with that, let me just put up a presentation. We'll move through that, and we will have some questions and answers at the end, so plenty of time to discuss. So bear with me a moment while I do that. Okay. All right. And Ramesh, if you could confirm for me that you are
Yes.
able to see. Okay, great. So let me just start here with an analogy that I think makes sense. And the analogy I like to use to illustrate this complexity of relationships and importance of these relationships between policymakers and other stakeholders who are not technical people in the technical community is to use a medical analogy. And think of yourself as an individual who obviously at the end of the day, you're responsible for your health. But of course, you're dependent on a lot of other things to achieve that goal. You know, the medical community, food networks, water treatment networks, all these different networks influence that. As relates to medical care, a lot of what you need to know about your health comes from different sources, whether it's looking at the contents of a food package or whether it's getting the results of a medical test. And each of the areas that are important for you to understand your health are well monitored, well measured, often well regulated, typically, and you get information in all those areas. But the key area here that's challenging, and this is where the analogy lies with the electric power system, is as the individual patient, it is left to you, for the most part, to integrate the information and the advice and data that you get from different areas. So you might get a blood test result. You might be looking at dietary management and looking at food content. You might even be considering where you live, all driven by a desire to achieve health outcomes. It's left to you to figure out how to integrate what you know in each of those areas into a holistic framework that allows you to make decisions about your health. That's very challenging, considering that each of those areas contains considerable technical depth and complexity. That's very much the same as the electric power system. Obviously, as individual consumers, we all want and need electricity. We need reliable electricity, cost-effective electricity. We have our economy, national security. There are so many aspects of our society that are dependent on electricity. Yet the policymakers who are tasked with making decisions as it relates to that system are faced with interpreting tremendous amounts of information from a wide variety of experts and studies and direct data coming from these different infrastructures. That's very, very, very challenging. And I'll elaborate on this further as we go into this, but the key message I want to convey here and go into a little bit of depth about is understanding the system and understanding where the relationships with different stakeholder groups reside, so that as you all pursue your work, whether you're actively working or whether you're embarking upon a career, whether you're still in the educational phase, you recognize, how am I going to manage the ability to communicate with the different stakeholders that are important to the area I'm working in. That's just, I can't emphasize enough how critical it is to place that at a high priority in your own efforts to work in electric power. So that's the analogy. So let's apply that a little bit. So first of all, let me just kind of an overview. My understanding from Ramesh is there's some diversity of people that might be on the call today. So we're going to go over the power system just a little bit. Some key features and characteristics. So with this diagram here, there are lots of these types of diagrams, and it may look a little bit complex for those of you who are not familiar with the power system. But in essence, what you have on the left is you're generating power. You're taking a primary fuel, nuclear fuel, coal, natural gas, wind, and you're converting it into electricity through a generator. Okay. And then you move that electricity through wires to ultimately to a consumer, which is sort of shown on the far right-hand edge. Those steps of moving that electricity from a generation point to the consumption point involve a variety of technical complexities. You need to increase or decrease the voltage of the electricity as it moves to different parts of the transmission and distribution network in the interests of safety and efficiency. And each of these sort of diagrams that you see in this picture contains a whole domain of technical challenges and policy requirements and regulatory requirements. And so It's a very complicated and diverse array of domains, each of which carries with it a variety of policy questions and regulatory requirements and so on. So I think we could obviously delve into these in greater depth, and I'll be happy to answer questions about some of these things if some of you want to do that. But I think the most important thing here right now to understand is that there are several steps in the process of generation and ultimate consumption, and each of those steps contains policy questions and regulatory questions that have to be addressed, and very important technical questions that have to be resolved in order to inform the policy decisions that occur. That's the key idea to recognize here. And the last comment I'll make is obviously there are some substantial geographical distances involved in this network. It's not very highly localized. It can be very distributed. So an overview here to just sort of maybe add some more descriptions. I've already talked about sort of the basic generation, transmission, and the consumption. Another important thing to recognize here are the last couple of points. First of all, the whole network is interconnected. And the analogy I like to use with people is that some of you who may have experienced this. If you've ever lived in an old building where the water system is designed such that when people start to turn on water in different parts of the building, other people can see a change in water pressure or water flow. Our whole system is very much like that, even though we have degrees of more or less connection in different parts of the system. In aggregate, whatever happens one place in the network creates some degree of an effect elsewhere on the network. And that interconnectedness creates some interesting challenges with respect to operations and reliability and safety. And plus, that translates to some policy questions because policy is aimed at guaranteeing the sustainability of the system in terms of its cost, in terms of its reliability, in terms of its environmental impact. The other part of it is that although there's a great deal of research focus and there's a lot of entrepreneurial activity and business activity in this area, our system pretty much doesn't have a tremendous amount of energy storage, which means that the amount of energy we're consuming at any given time almost entirely has to be met at that instant in time by generation somewhere that's producing that energy. We don't have much of a buffer between what we produce and when we consume it because it's a just-in-time system. To give you an idea, I actually recently just checked on these numbers. It's interestingly, they haven't changed a great deal in the last 20 years. But roughly speaking, the United States system has on the order of 2+% of storage. So if you look at our total ability to generate electricity, maybe their storage equivalent to about 2 to 3% of that that's available. In Europe, for example, in the Western Europe and that part of the network, due to the availability of hydro resources and some different topology of the system, they have about 7% of storage. But when you have 2% of storage in a system as large as the United States, that essentially means it's a just-in-time system. When a light switch gets flipped on, someone's got to generate more electricity somewhere. That creates also a very complex set of challenges, which leads to needs for regulation and policies and so on. So that's very important things to recognize with this system. Let me back up and say one last thing. I'm not going to spend time on that today, but maybe in next semester we will talk more about it. But there are some interesting questions about, well, what research would we need to reverse some of these limitations, such as the storage question? And the storage area is a very important area of research because should we be able to create a significant amount of buffering between when we generate and how much we generate and when we consume, that would have profound positive implications for how we operate the system. So that's very much a fruitful area for future research. Okay, so just some other key challenges I think it's important to understand in terms of how the system functions. The first is, as we were talking about earlier, electricity is essentially an essential infrastructure, and it's indefinitely that way. So whatever we do in terms of policy, in terms of operations, in terms of technical solutions, you have to envision that those policies or technical solutions are viable for the indefinite future. So that's quite a challenge. When you start to think about the very long-term implications of a technology or of a policy, it changes your perspective a great deal if you realize there's no real horizon to it. The second is that we have the added complexity that different parts of our consumption vary. Industrial facilities and when and how they can consume power, very different than when residential consumers consume power. And because we have a just-in-time system with not much storage, the implications of differences in load patterns is important. and challenging. The stakeholders involved don't all necessarily have the same goals. Some stakeholders are very much financially driven, and that's pretty much what they're out there for. Other stakeholders are balancing, say, reliability and economic priorities. Other stakeholders, say, for example, the National Electricity Reliability Council, NERC, is almost entirely focused on reliability and safety. So those competing priorities sometimes clash, and that creates problems for the regulators and the policymakers in terms of how they establish policies so that those conflicts are appropriately balanced. As I said earlier, we have the just-in-time power delivery challenge. Another variable that's interesting, particularly as it relates to natural gas, is that some of the resources we use in the electric power system, water would be the other resource, are used for other non-power related things. And as our economy grows and our population grows, the competition between the electric power sector and other sectors for resources increases. And that requires prioritization and decision-making. A classic example that those of you who may be familiar, the cold snaps we had in Texas more recently, and then actually had another cold snap several years prior to that, where natural gas was needed for heating, but also needed for power because Texas grid is heavy in natural gas, along with renewables. That decision-making on how you manage that competition, especially in critical situations, is a domain for policy, and policymakers need to understand how the power sector functions in order to make those decisions well. So that's a specific way in which you see a connection. And then finally, another thing to recognize, simple yet inexorably true, is that in the long run, electricity consumption is proportional to population, and our population continues to grow. So even a very, very low rate of growth in consumption over a long period of time can compound of substantially larger amounts of demand. And so that means that the system will continue to add capacity. The system will continue to add transmission networks. There will be more complexity. That's both a technical challenge, and it's also a challenge for policymakers and regulators to understand and to provide policymaking that makes sense. So that's a domain in which communication between the policymaking community and the technical community is very, very important. Understanding the implications of adding resources and how that's done. Okay, so let's see here, a few other system concepts that I wanted to introduce that are kind of maybe a little bit beyond just technical. The first is that a lot of the assets in the system are not owned by the same types of organizations. And broadly speaking, there are private owners of some things. We have a lot of private owners of distribution assets, people that own their own diesel generator or own their own solar panels. But the vast majority of power and the assets for transmitting electricity are owned by some type of utility organization. And those organizations divided into three groups. By the vast majority are investor-owned, companies with stock in them, like American Electric Power, okay, which is based centered in Ohio and that region, or government-owned utilities like the Tennessee Valley Authority, or a third one would be like cooperatives. They don't own a large portion of the capacity, but there are many, many of them, especially in rural areas. Each of these different types of owners have somewhat different priorities as far as the types of customers they serve. And so there are some priorities that regulators and policymakers have to manage when they're considering these different types of owners. And as I noted here, there isn't really a quarterback for the whole system. All these different organizations that own different assets have to figure out ways to coordinate with one another because the system is interconnected, even though there isn't a singular authority overarching everybody that manages that coordination. That's a challenge. And we'll talk about markets here a little bit further on. We have introduced deregulation into the power system back in the, I guess, probably the early 90s or so. The idea being that markets self-optimize and we would see a more efficient delivery of electricity. That has happened in some ways. In other ways, it has had some unintended consequences. But it has created an added layer of complexity because now markets create added layers of requirements on generators and on how energy moves from generators to middlemen and distributors. And then there are, of course, the final reality is that the energy sector, and specifically electricity, is a domain in which often federal and state governments implement policies which are aimed at incenting or impeding investment in different ways. And those motivations are often economic or environmental. They're not always purely in terms of what makes the electricity system work better. So you see policies introduced which have these other objectives. And then I just want to mention here finally that independent system operators are organizations which are designed to coordinate subsets of the grid as it relates to the actual function of the system and the operations of the markets. And there are lots of complexities in that, which again introduce another layer of challenges for policymakers in terms of rules that relate to how markets operate or cannot operate, which again creates an important priority for the technical community to do a good job of helping policymakers understand how the system operates so that those policies can be made in an informed way. So already, just in these few slides, I think, if I just go back here to this diagram, there's a lot of complexity you can see in just these 4 slides. We've picked up quite a few ideas that create a lot of complexity. You can imagine that you're a state assembly person, you're a regulator at a state or at federal level, or you're a congressperson or a staffer working for a senator. How are you supposed to understand all this? And when generally you're doing many other things. So, and this is why I say that it's so important for the technical community to take on the responsibility of trying to create a way to communicate with the policy community so they can understand it. And if we fail to do that, we will get policies that are not well informed, and we will have unintended consequences. And we've already seen that in the past. So this is definitely something I think the technical community has a responsibility to address. So I wanted to put up this slide here. I guess this is another shock and awe slide on complexity, but what I really want to illustrate here is, this is a slide that I got from EPRI. It was put together back in 2017, but what it really shows is all the levels at which the electric power system attempts to manage issues that relate to the reliability, simply the availability of electricity. And the most important thing, I'm not going to go through this slide and describe in every detail, but simply to recognize 2 things. Or 3 things. First, that technically speaking, the voltage and the frequency of electricity are important parameters to manage. They have to both be managed in narrow tolerances. That's the first thing. The second thing is the time scale over which you have to manage those things. So there are longer and shorter time scales over which those things have to be managed, and each of those time scales requires its own set of strategies for managing those things. This diagram illustrates some of those domains in which control is needed. All these acronyms and things are complicated, but they all refer essentially to different types of control of voltage or frequency within certain time domains. And the third thing to recognize is the system is a system. It has inertia. If you turn off all the power plants right now, there is going to be some residual inertia which will continue to deliver electricity for a few seconds or minutes. That inertia plays a very important role in understanding how the system behaves in response to changes in load, weather-driven events, the loss of a power plant. It's very important to understand that. And regulation and policies that relate to the system, therefore, have to recognize understanding of that. So this is just kind of illustrates the challenge that we maybe have in the technical community to create a way for policymakers to understand where the most important issues are and how to frame those issues so they can make decisions as it relates to policies and regulation. Another perspective, I've been using this slide for a few years based on Ramesh's suggestion, which is really good, is this is a perspective on who are the stakeholders, who has a stake in the game. Obviously on the, and one stakeholder that's not even mentioned here, which is the overarching one, is the consumer, the people that need the electricity, ranging from the individuals to the small business owners up to the industrial consumers. These stakeholders here are all involved in the process of providing electricity or advocating for the ways in which electricity is produced and delivered. So you have utility companies, I mentioned those earlier. You have all the public sector, the policymakers, basically the regulators and other agencies which have a role in how electricity is developed or delivered. You have the system operators who want to make sure the markets work as well as the systems themselves work. You have investors, independent power producers who own their own assets, investors who want to own and develop an asset, but not for a long term. So they're maybe less interested in the long-term sustainability system than they are on what their return on investment is going to be in a matter of, say, 5 to 7 years. And then you have a wide assortment of advocates who are motivated by reducing costs, by reducing environmental impacts, by prioritizing one technology over another for various perceived benefits. Those are all acting on the policymakers at all times. So this is and these policymakers these stakeholders interact with one another. as you can see through the sort of the diagram here, in various ways. That's a complicated environment also, in which a policymaker has to function. And so it's very important to, in the technical community, to recognize what's motivating these different stakeholders and recognize where technology can provide a solution which balances the needs of different stakeholders. The degree to which we in the technology community can do that, the more optionality we provide to the policymakers to find ways to make a coherent policy. So that's another connection that's important to recognize. I've kind of summarized here in words a few aspects of what these different stakeholders are driven by. What I kind of want to emphasize is a couple of key points here that play a major role. The biggest one, I think, is at the very top there, and that is cost. If you look historically, I've been working in the industry since the late 70s. Cost, in the end of the day, cost, because it's quantifiable, it's can be it's quantified, is often, if it's not the only driver, it's by far the dominant driver of decisions at a lot of levels. Investment decisions, decisions on a lot of policies are driven by, well, what reduces the cost to consumer in terms of just dollars and cents. Often it's even the instantaneous cost, like what the cost right now for a kilowatt hour is might be more important than what the average kilowatt hour cost is over 30 years. That is often the case because cost is the most easily understood parameter by policymakers. They understand dollars and cents, even though behind that figure may be a lot of complicated calculations. So a challenge we have is to figure out how to enable policymakers to see the impact of other important considerations which are not as easily quantified. And we'll talk briefly. I think those of you who've seen some of my earlier presentations have seen me talk an awful lot about energy economic modeling. That's an avenue where you can help policymakers see the impact of other key considerations which are more not as easily quantified. Environmental issues and social goals, minimizing public health impacts and so on, is usually achieved through a regulatory domain. The key there is helping policymakers balance the achievement of those goals while looking at the cost and reliability impacts that those policies may create. I think the other comment I want to make is I said earlier briefly that sustainability of the power system is so important indefinitely. This is not the system we can say, well, I've got a solution that's going to work well for 20 years. You really have to say to yourself, whatever we do, we have to place the expectation we're trying to make this work indefinitely. Although that's true and generally widely recognized, in practice, there is no real singular organization or stakeholder or government agency that owns that. What typically happens is that utility companies, who are the principal owners of most of the assets, they worry about that for practical reasons. But there isn't really any guarantee that long-term sustainability will be achieved. Therefore, the ability of making policymakers able to understand the implications of the need for sustainability and therefore the implications of policy options is a tool to help ensure sustainability. And therefore that burden of making that communication clear falls back on the technical community as it interacts with the policymaking community. It was believed that markets would eventually create a level of efficiency that would sort of intrinsically take care of this. I think that's proven not to be true, mainly because the markets don't monetize all of the aspects of value that electricity has. And because they don't monetize all those aspects, some of those aspects get neglected when markets self-optimize. They optimize around just the basic cost of electricity, but not necessarily around, say, other issues like availability and reliability. Okay, so what we have now is a very complicated mix of regulatory and policy conditions at the state and federal level. And that probably is going to be that way for a very long time. I would say the backdrop of my overall presentation is to simply encourage all of you to engage on this topic and help over time get that environment simpler and more understandable. It's not going to be something we achieve very quickly. There's a lot of these competing stakeholder priorities are going to always make it difficult to achieve the level of simplicity and clarity that we all need. But it's a very important priority to retain. Okay, so kind of coming to policy here a little bit more. I think the way I thought about it, one way to think about looking at this is there's decisions that have to do with investment. You know, do we need more generation? Do we need more transmission lines? Do we need to put more of the distribution system underground instead of overground? You know, lots of those kinds of questions. Those questions are you know, both economic, and they also have other, you know, impacts on local communities and on maybe environmental issues. So policies that create boundaries, let's say, for how those decisions can be made or are made, is one whole space in which policy needs to be informed by the technology community. The other side is decisions that relate to other aspects of sustainability besides cost or the amount of energy that's available. You know, the asset investment kind of deals with cost and deals often with, do we simply have enough capacity to produce electricity we might need? The other side is, well, how do we ensure we're going to have the reliability and availability we need? How do we do that while continuing to meet the environmental goals we've already established? How do we do that while achieving stringent new environmental goals like greenhouse gas emissions reductions or zeroing out those emissions? That is a very complicated area in which individual policies have surfaced, but they tend to be very targeted policies that aren't necessarily connected to, like, you might see policies made about reliability, or you might see policies made about greenhouse gas emissions, and they may not really, they may actually harm one another even. You know, for example, some years ago, the Environmental Protection Agency, during under the Obama administration, I believe, in the first, second term, but there was a proposal to reduce coal generation in the United States, and there was an approach for doing this that involved some calculations of coal emissions. Anyway, the important comment is there was a very regionalized approach to doing this, which at certain regions resulted in the desired goal of reducing coal emissions, but in aggregate actually could create more greenhouse gas emissions by virtue of adding up the impacts in all the different regions. So it's a very complex environment in which to address these other aspects of sustainability. And that is where some kind of a framework for policymakers to understand the options and decision impacts is needed. And that we'll probably talk about a little bit more here. And I just listed, you know, some of the different groups that are, of course, interested in that aspect of things. So I'll stop for just a second. I'm sure a lot of people probably, you know, head spinning maybe a little bit when you start thinking about all these dimensions. There is a way, I think, to reduce this a little bit more and get this towards more manageable. So don't lose hope completely here as you're listening to this conversation. Okay, so here I just attempted to kind of define in a holistic or a comprehensive way, what do I really mean by the word sustainability as it relates to electric power generation? Obviously, we want to be cheap. We want the cost to be stable, not volatile. We want continued investment to be enabled. Obviously, we want it to be safe, want it to be reliable, available, and we want to run for basically indefinite future. And we want to reduce environmental impacts in many different ways, including maybe new ways that we're just beginning to reduce, as well as reducing public health impacts. So sustainability from an electric power standpoint means achieving all of these things for the indefinite future. And so that's the thing to keep in mind, as opposed to maybe the more conventional way of thinking of sustainability as an environmental thing. It's much more than that as it relates to electric power. I think I've already kind of clarified why sustainability is very important, but I will just simply say that, you know, I may point out a couple of other things I haven't mentioned yet, maybe that are important to keep in mind. First is, because we are still basically a growing economy and a growing population, we're going to have more impacts or more challenges as we increase the amount of electricity that's produced. So sustainability has a high priority as we anticipate how do we absorb more growth in our system over the long term. And again, I think you have to have a multi-decadal time frame as you think about this. The second is that many studies have shown this, but ultimately addressing greenhouse gas emissions as it relates to the entire US economy will almost certainly entirely depend on decarbonizing electric power generation. Very few scenarios exclude that as an option. Therefore, I think you can safely assume that decarbonizing electricity production will be a prerequisite for a broader addressing of greenhouse gas emissions, and therefore it's a very important element of sustainability. Another thing to keep in mind is that electricity is Although we have a storage issue, as I mentioned earlier, obviously we have batteries on small scale, but electricity is a very fungible type of electricity form. You can run motors with it, you can heat with it, you can do many different types of tasks with it. Other primary fuels are less fungible in that sense, and that makes electricity economically very valuable, which is why the level of electrification of our economy has steadily grown over time, which emphasizes again why the sustainability goal is so absolutely critical. Okay, so let's move on. Let's see here. On the key challenges, I think if we talk about timeframes and the difference in demand and load patterns, let me just touch on the last point on this slide, which I think is something we haven't talked about in depth, because I think this is another important part of it. The markets that we currently have are mostly driven by how to achieve the most cost-efficient electricity production possible. When they first were created, the markets almost entirely did that, almost without regard to anything else. And very quickly, very quickly, people realized, well, we have to have extra capacity available for peak periods of generation. How do we ensure that a power plant runs so that it's available when needed, even if it's not needed all the time? And so after a time, people started to modify how the markets are designed to create an incentive to have capacity available. And so the capacity markets came into existence. On top of that, several different jurisdictions decided to mandate certain levels of generation from renewables for to achieve environmental goals, which created a secondary effect of we have to make room. If the market doesn't need all the capacity that's being generated, you have to incent some people not to generate if it's a period of time we need to be taking a certain amount of generation from renewables. That required the creation of some additional market features to allow that to happen. With all of that, still, some systems can increase or decrease power output more quickly than others. And the reliability of the system depends on operational flexibility as well as on total capacity. And so they began to realize that we need to sometimes incent certain types of assets to run or be available so that we can achieve our reliability goals. And that resulted in the creation of additional features in markets to do that. This has made the markets very complicated as a result of these added layers to address some of these other issues. And markets are something that are subject to regulation and policies. And so it's created a connection to the power system with the policymakers through the medium of how do these markets, or how are they structured, how they operate. And this is typically very often at a state level this occurs. So this is another connection point through which policymakers connect to the power system through the structure and regulation of these power markets. So, okay, so I just want to take a brief look here at, okay, lots of challenges, lots of problems. So what does that all mean? And so this is kind of a little bit technical, but I just want to give a quick peek into what can be done to address some of these issues and also maybe make it simpler to make decisions. Well, first, I've sort of roughly put these in kind of a rough order of what I think of as challenging, not just technically challenging in terms of scope. So at the top end there, the green, we need to keep reducing the cost of operating our units and making them as maintainable and long-lived as possible. And there's a lot of research, as Ramesh can tell you, that has been done in that, and that's very valuable, and that should continue. And that creates, the more we can do that, the more we can utilize the momentum of the existing fleet of assets we already have. Increasing the lifetime of generation plants is very valuable. And a lot of work has been done in those areas, and the opportunities exist for natural gas, for renewables, and for nuclear. And that work is ongoing in those areas. That will give us more options. This third point is an area which I haven't talked as, I've only alluded to it briefly, but it's a very important tool, I think, as it relates to policymakers and the interaction with the technical community. A lot of work has been done in energy economic analysis historically to simply answer the question, how do we produce electricity most cheaply? When you consider, the different number of regions, the levels of interconnectivity between the regions, and the types of different power plants we have. And originally, a lot of those analyses were asking the question, are we better off pursuing a selected set of generation technologies? They have evolved, though, to become a much more sophisticated set of analyses, which ask the question, given a set of regulations, and given the availability of different types of technologies, both for transmission distribution as well as for generation, and given that some of these policies address environmental goals or invest reliability goals, how do we figure out what the most economically efficient mix of technologies is to achieve all of that? Now, doing that in a totally reliable and transparent and comprehensive way is not easy, and a lot of research continues in this area of energy economic analysis, but it's a very fruitful direction because a lot of these tools are able to produce results which allow policymakers to visualize trade-offs and impacts of specific policy decisions. And I came to realize in my years, especially with EPRI, that and enabling them to understand the dimensions of a problem and understand the trade-offs in a simple way was as important as convincing them of the technical reliability of the work that's being done. And these energy economic analyses are very, very powerful tools in doing that. There are some challenges that remain, looking at longer timeframes, accurately representing some of the technology opportunities and limitations that different technologies have when you're representing them within the framework of the analysis, and understanding not just what's most economic to put into the system over many decades, but understand the instantaneous drivers for why certain assets are dispatched and used or not. But connecting those two is also challenging. So those are areas of research, but that's an important area of research. That's an opportunity to address some of these communication challenges I've been describing. They're making more power plants more flexible in terms of output levels, and changing output levels fast is going to be very valuable. That's a whole nother seminar really, and we can talk about that in another seminar, but that operational flexibility is a key asset in increasing the capability of the system to meet the disparate aspects of sustainability I've mentioned. And I've listed a few different examples of what operational flexibility means for different types of technologies. The acronym HRSG stands for Heat Recovery Steam Generator, which is a critical component in natural gas combined cycle units, which allows you to use the waste heat to create steam, which can be used. The other thing is recognizing that, hey, for a given amount of physical space, a given amount of water consumption, how can we increase the amount of energy we get out of a given amount of consumption of those precious resources? And so we can do that by increasing capacity factors. More nuclear generation, nuclear is very high capacity factor, higher capacity factor wind and solar plants. Storage, I should have mentioned that here, but if you have more storage available, you can then use a lower capacity factor asset to generate power on a more ongoing basis and simply capture the energy. Making CO2 capture and storage viable and economic would allow us to use fossil assets, which we're now phasing out. Although we use a lot of natural gas now, ultimately to decarbonize the electric sector as it stands today, we're going to have to get rid of natural gas, or we're going to have to utilize very expensive CO2 capture and storage technologies and increase the cost of electricity produced from the natural gas assets. So improving the cost effectiveness and operational flexibility of CO2 capture and storage systems will really have a tremendous value in giving us more options in terms of using fossil assets and achieving overall decarbonization, which will make the system much more capable of achieving sustainability on the broader perspective that I was describing earlier. And then finally, the big hitter, and this really goes to storage I mentioned earlier, is decoupling generation from storage, getting to a place where you're not a just-in-time system. You can produce electricity when it's most efficient, most environmentally least impactful, and then consume it at different times. They don't have to be coordinated. Storage will help to do that. More interconnectivity within the transmission system will allow us to move power from one place to another, so we can take advantage of power generation in one place and consumption in another place. The timing will be better. And recognizing that we can change how we operate the units themselves and how we operate markets in order to manage how energy is consumed, sort of aggregate loads and get them to, many of you are familiar with like Nest thermostats, which say, well, for a little bit of credit or money, if you let us knock down your thermostat setting by a degree or increase it by a degree, that gives the utility some flexibility in terms of reducing energy needs. Expanding that idea on a much broader basis will help us decouple generation consumption. That's a very challenging problem to overcome, but if overcome, it would have a profound impact on how we would be able to achieve overall sustainability and give policymakers more options on how to establish coherent policies, because the system would have more capabilities. All right, so I'm final slide here, and then we can have discussion. So first thing is the sustainability of the capital S. It's all these different areas: technological, economic, environmental. We do, as it stands today, we have a problem in that we haven't really, as a society, figured out how to quantitatively and explicitly value aspects of assets that deliver valuable parts of sustainability other than reduced cost. We don't consistently value the reduced emissions of greenhouse gases. We don't consistently value reliability or availability or operational flexibility. I mean, we do in certain markets at certain times, but as a whole, those things are not systematically and regularly valued. And until that's done, we will have a hard time achieving overall sustainability. And what that translates to as it relates to policy is policymakers are still tasked with addressing those priorities in some way through policies. And if we don't have markets and models which show how a policy impacts the achievement of those things, it's a very difficult challenge to make coherent policy. Obviously, a lot of variables can change. Environmental goals change. Economic conditions can change. Fuel costs go up or down. Consumption can go down or up for a period of time. Political conditions can change. And so the framework in which we communicate with policymakers has to be capable of looking at the impacts of those changes. It's very hard, again, for policymakers to do that without expert input. This modeling and optimization I was referring to earlier is really, really a powerful tool. And I strongly encourage anyone who's interested in the electric power system to understand the role that kind of modeling plays in making investment decisions, in advocating policy positions, in communicating to policymakers. I think it will really enhance your ability to understand the role of your research or your technical activities if you do that. And finally, the last bottom line, if you take nothing else from this presentation, the goal here is to look at policymakers as people, as a customer, someone you're trying to help them understand the variables so they can make an informed decision. Helping them do that is a responsibility of the technical community. It's not policymaker responsibility because we're the ones who have the knowledge to do that. So I realize it's a lot of layers of complexity, but that's my goal, is to make people understand what we're dealing with. So with that, I'd like to stop here and open it up for any comments or questions.
Terrific. Thank you, Revis. And this is kind of a preview of one of the topics you'll be touching upon next semester. As we have done in the past, I would like to have the students go take the first shot at asking questions of the speaker. So students, if you can unmute yourself and introduce yourself and ask that question, please go ahead. Questions for Revis? Unmute yourself, students, and if you have questions, please ask them or put it in the chat box if you're shy. So, Revis, as we wait for the Q&A session from the students, you know, our grid is very much driven by a federal policy, but the states have a lot of say in the matter. It varies from one state to another. And unlike, say, a country like Germany or France, for that matter. So what are your thoughts on having an overall federal policy in the US similar to what's there in Europe, and what's the pros and cons, you think?
Okay, that's both a dangerous and a complex question. Dangerous in that has political aspects to it, but let me try to address it from a technical perspective. You know, I'm not going to make political commentary here, but I think it's certainly easier to, I think, recognize where the critical issues are and connect those issues to policies which address those issues and coordinate the collective impact of multiple policies if there is a central authority, a federal level, for example, or if, if each state had 100% control. I think the danger, unfortunately, is there is a danger. The danger is that when you have a singular level of authority looking at these problems and looking at policies, if a decision is made to over-rely on a technology or to over-rely on a particular policy, and it turns out that there were unanticipated challenges with doing that, it's a little easier to make a mistake, so to speak, that's hard to recover from. We have some definite problems with the diversity of jurisdictions we have in the United States, but there's a certain level of resiliency that comes from the fact that we have a lot of different groups of people looking at the same problems and trying to make sure they're properly addressed. And so we're a little less susceptible perhaps to a single approach that may turn out to have some aspects that have overlooked some challenges. Obviously no one's going to completely overlook obvious problems, but like I can give you one quick example. France generates about 80% or so of its output from nuclear power. So that's been generally, I would say, probably a big plus in the balance. But there have been a few pretty big challenges. One of them is that, every so often they have a heat wave in Europe. They had one back in 2003, and they just had one this past summer or the summer before, to a level where the rivers and lakes, which are the heat sinks for these power plants, their temperatures raised to a level where they have to reduce the output of these nuclear power plants. Well, since those power plants are by far the dominant source of electricity, that creates quite a challenge for meeting demand when that happens. So that's somewhat of a consequence of a choice to, at a high level, to say we're going to really rely on, mostly on this one particular technology. So that's an example. And you could argue that those situations arise infrequently enough that maybe the positives outweigh the negatives, but that's an example. Another might be if you have a technical challenge related to a technology that's being deployed, that since you use it everywhere, that technical challenge could affect a large portion of your system all at the same time. So those would be my perspectives.
So we have a question in the chat box from David Olen Riolaju. Can there be some other redundant solution if a large part of the generation system in the US fails at once, considering the JITP system and 2% storage capacity you talked about? JITP.
I'm not sure what JITP is, but just in time, probably just in time production is what he means. Yeah. Well, I think I'm trying to think of the core question here. Is there an alternative? I think there are two, broadly speaking, I think there are two, maybe two or three strategies that you can employ. One, of course, is storage. If you could increase the level of storage in the system to a much larger level, and you can ensure that it's geographically adequately distributed, you might be able to really buffer much more effectively the loss, a significant loss of some key assets in certain parts of the country. That would be one challenge. Right now, battery technology is just not scalable from an economic standpoint. It's extremely expensive. And so as yet, that hasn't proven to be a grid scale solution widespread, although there are batteries used in the grid in select cases. The other approach is, pumped hydroelectric power, pumping water uphill and let it go downhill. That's been one of the most preferred methods if it's available. That's a function of topology or geography. And a lot of the resources that are available have been developed. Those other sites that are available but haven't been developed, there's a lot of environmental opposition to that. Essentially, building one of these things is not much different than building a dam. It's very, very extensive and invasive type of a project to build one. So there's been often resistance to doing that. So so one dimension is more storage. Another dimension would be more transmission system interconnectivity. If say right now, for the amount of capacity we have, the accessibility in any part of the country to additional power from another part of the country is hampered by the degree to which we have interconnectivity. We don't have uniform interconnectivity everywhere. It's high in some parts, lesser in others. Across broad regions, the general connectivity is less. You can kind of divide the United States into 4 or 5 major sort of interconnections, they call it, in between which there's relatively lesser connection. So more interconnectivity strategically placed perhaps would be a way to relieve susceptibility to a major outage. And then the third potential idea, I'll stop with this one, which I think is a little more uncertain, would be perhaps if there was an ability to increase output from some assets which are not operating at full output or not operating at all more rapidly, it would be a way to mitigate the propagation of a disturbance, which otherwise would result in the loss of many assets. So that's more maybe a time response solution than it is just capacity related solution. So those are the thoughts that I would offer as possible alternatives.
Thank you, Revis. David, if you have a follow-up question or you had some other doubts, please go ahead and unmute yourself and ask a question or put your question back in the chat box. Again, questions from the audience, the general audience. Please unmute yourself, introduce yourself, and ask a question, please. Questions for Revis? So Revis, something that we talk about in our class, looking ahead. There's some challenges where we need to change, our generation capabilities, much more carbon-free, if not zero carbon. And of course, these targets need to be achieved in the next couple of decades. So what are your thoughts, even if we achieve the technology targets that we are truly carbon-free, what kind of impact do you think it has on other aspects, human behavior, how we go about doing our business? We don't think twice about jumping into a car and what if all the cars aren't electric? Any thoughts looking ahead? What are the other things that would be important in how we manage the grid? Right now we have a number of stakeholders. Is that going to increase dramatically?
Yeah, I think that's a complex multi-part question, I'd say. But first, I'll just start by saying yes to most of your what ifs. First, I would say that the number of stakeholders is going to increase because as electricity is more deeply connected to other areas, transportation mainly, and we always all think about residential or private vehicles. Often we think about electric vehicles, but the big win, if it can be achieved, is to penetrate the distribution system. Our United States doesn't depend on rail. We just depend on trucks and vans to deliver products to people and services. If that is decarbonized substantially through technology and availability of recharging stations and all the other things that would have to happen, that whole part of our industry, which is very important, the whole community of people that the business of distributing products and services, they're going to become stakeholders of the electric power to a larger degree, and they're going to have interests and desires and things, and that's going to be challenging. Probably, I'm speculating, but I would say that is a very diverse environment of individuals. So I think there'll be an increased pressure to focus more exclusively on cost as a result of that. So that's one thing I would say. As far as behavior is concerned, that's a very broad question. I'll just offer two perspectives that I would have. One is that I think in general, we're going to have to accept the inevitability that electricity is going to be more expensive. Because number one, because there's more of it being used, but also as we place more limitations on electricity, we don't want to adversely affect the environment. We want to only produce electricity in certain ways or from certain resources. We're going to introduce more technology to meet those needs, and that will create cost. Sorry about that. That'll create cost for consumers, and we'll see that. So I think that's another inevitability, and how behavior will change as a result of that. People will seek ways to reduce or avoid that cost. I don't know if that will maybe result in different patterns of energy usage, more interest in distributed resources, at the business level, or things like solar panels at the private level, whereas before it would be seen as too expensive. There's going to be a reaction there.
I'm reminded of the lecture that we heard from an every person, Abhijit, last week, and he introduced a metric or measure of amount of energy. He called a cubic mile of oil. Sorry, cubic mile of oil. And just to let you know how big that is, the world consumption is roughly 10 cubic miles of oil presently. And so what he mentioned to the class was really startling to me, that there's still 1,500 cubic miles of oil reserves of coal, which means 150 years. It's very tempting,
Yeah.
if it wasn't controlled, to go and dig for that coal, and we know how to burn coal to generate electricity. I mean, that kind of discipline, I mean, it just staggered me that the reserves are so enormous.
I mean, again, tapping into a resource that has a high cost of retrieval and a high cost of delivery when you consider environmental and other constraints that you want to use it for under, it just becomes a matter of cost, a cost point. I mean, like right now, natural gas, although it's kind of back, the prices are back up now, but for the last 10, 20 years, we've seen some low natural gas prices, particularly with fracking, emergence of fracking. So there's a tendency to migrate to that resource, and it's more acceptable to ignore others. I think in the long run, we will be faced with needing to utilize all the resources that we have, just simply due to the sheer size. The other thing to keep in mind, this is a global comment, but nearly half the world, or a little more than half the world, basically doesn't use electricity still. A very large fraction of the human population in the world doesn't use electricity. Well, when that happens, that's going to eventually change, and that's going to increase the competition for resources globally. And so I think you're going to see those impacts will surface. Now, that's not going to happen in 5 years, obviously. That's going to happen in many decades. But to my point earlier, the way in which I think when you think about the electric power sector, when you think about sustainability of technologies and sustainability of policies, is on that time frame. And in that time frame, global competition for resources will increase. And so that will make it more attractive to consider using resources that we previously felt we could choose not to use, such as burning coal, using very expensive CO2 capture and storage, reducing the level of power output to a level where we can successfully manage the CO2 capture, and diverting some of the energy to recovering that CO2 and sequestering it or using it, which further reduces the amount of useful energy that comes out of the power plant. That eventually may become something we'll accept.
Well, please go ahead, and if you want to ask a question of REVIS, please unmute yourself and introduce yourself. But meanwhile, there's a question in the chat box from Oshan, a student. Oshan asks, as you highlighted, REVIS, investment decisions are predominantly based on cost, and initial costs rather than life cycle costs. How can we address the fact of quantifying other non-financial factors in the decision-making and policy-making?
Thank you for that question. I think it allows me to elaborate a little more on this modeling topic I was referring to earlier. During the final 10 years or so I spent at EPRI, I was pretty deeply involved in a lot of this energy economic modeling work as an engineer, contributing to some of the technical inputs. And when I discovered there, I think goes right to your question. What you could see is if you could postulate, well, if I have a power plant that provides a certain high level of reliability, then in these models where you can not only model the cost of production, but you can also model the dispatchability of a power plant and how often it runs, you can start to see in quantitative terms the benefits of those characteristics. And that then enables one to if it's appropriate, place a higher value on an asset that can deliver value in those other dimensions. Because ultimately what happens is increased availability or increased reliability translates to more electricity produced at a given cost. So sorry about that. I've got a competitor in the audience over here. So anyway, I would just say that these models are a way to represent these other aspects of value in different types of assets and show what the impact of those attributes are on the final production costs from that asset and the sustainability of that production. And that is a way to create visibility around those things, which therefore allows stakeholders to see that. And then you can start to have a discussion and debate about the attractiveness of a certain mix of assets, whether it's more or less nuclear, or ever having coal again, or having natural gas, but with CO2 capture and storage, or whatever the discussion is.
Good. Questions for Revis? Please put it in the chat box or please ask them yourself. Through audio, unmute yourself and introduce yourself, please.
Good day, Mr. Revis. This
Hi.
is David. I was the one that asked the first question earlier. Okay, and thank you. Wonderful presentation from you. So this is my question. Because I am from Nigeria, and I'm just looking at the state of Africa as a whole generally. The level of electricity we are exposed to is kind of very low compared to other parts of the world, say Europe and Americas and all that. Like, for example, now in Nigeria, according to the IEA report for 2019, our energy supply per capita is about 14.4 kilowatts hour. If we have to compare that, to say America that has about maybe 10,000 plus per capita, we'll see that it is very low. And also here in Nigeria, the electricity supply is also very, very low. And we kind of focus on say HEP, hydroelectric power, and natural gas as our major sources of energy generation. So this is what I'm looking at. Like, do you think the world as a whole can meet the full energy transition into cleaner energy by 2060? Do you think it is something possible? I'm looking at other continents. Now, I'm not focusing on, say, the America or the more developed continents, but looking at, say, Africa. Do you think it's something that can happen?
Okay, so I want to clarify. You said, can it complete by 2060 a transition to nuclear, did you say?
No, to clean.
To clean energy, yeah, clean.
Net
Okay, thank you.
zero.
That's what I thought you meant. I just wanted to clarify that. 2060, that's 50 years from now. That's 40 years from now. Probably entirely to do that, no. I mean, realistically, I'm not sure that's possible. I think I'm giving you a very immediate first reaction, so I have to qualify my answer. But when you think about the deployment of assets, the training and necessity for the staff and infrastructure to support that, so you need parts, manufacturing, maintenance, repair. There's all these different infrastructures that exist underlying a power system. I think it might take all of that 40 years to develop. You could probably go a long way, though, towards that goal. It's particularly if you're focused on resources that are greenhouse gas free or nearly greenhouse gas free. As I was saying earlier, the emissions associated with natural gas, right now, they're half of what coal is, per unit of energy, roughly speaking. So for a time being, that's okay. But very quickly, I think I remember analyses that we did some years ago that suggested that by 2030, we would need to start substantially eliminating the emissions from natural gas. That's only less than 10 years from now. Now that was an analysis based on a number of assumptions that could be different now. But what I would say is that you probably would be looking at the challenge, if you wanted a completely clean generation, of how you would capture CO2 as part of continued use of natural gas. That is an area that I suspect could impact that time frame severely. I'm not sure how fast a cost-effective CO2 capture storage will be available, or you have to have more expensive CO2 capture storage. So I would say that would be a very challenging goal, but you could make a lot of headway in that time frame. So that'd be my first cut at an answer.
David,
All right, thank you for that answer. Also, why do you think could the world also, can we evaluate geothermal? Because when you put natural gas and coal side to side, you said natural gas generates about half of greenhouse gases compared to coal. So what about geothermal sources?
Geothermal is excellent. I mean, essentially the way I view geothermal is really not much different than wind, in the sense that you have to place the asset where the resource exists, and then you have to connect that generation asset to the system so that you can get the power to the load centers wherever they are. As with wind and as with solar, the value, because now, let me back up. Geothermal certainly has a more positive aspect in that the resource is constant. It's pretty stable. So you can count on whenever you want to run, you can run and generate, as opposed to wind and solar. But I would say that if you have resources and you can create an infrastructure, connect those resources to the load centers. If in a perfect world, if they're not too far away, that would be ideal. You could more likely to develop it more quickly if that's the case. Also, if you have an existing network you can tap into, like we do in the United States, obviously that's one reason why some of the geothermal assets have been able to be incorporated relatively easily. I would say interconnection is probably the biggest thing there because you have to go where the resource is located.
All right, thank you.
You're welcome.
David's question kind of raises, you mentioned in a lot of parts of the world where electricity is, not even available. And unfortunately, it is a lot of Africa. And, I remember reading in the newspaper some time back that there's this huge deposit of fossil fuels in the Democratic Republic of Congo. But that would upset, make sure I get this right, the peat forests, which are big carbon sinks. And so the argument that most people make is that, well, that's another source of carbon sink that we're getting rid of, just like what's happening in the Amazon. At the same time, they have access to fossil fuel, which can increase prosperity. How do we argue that, no, they should not do that?
Well, I think, well, first of all, yeah, I mean, this, of course, is a longstanding question. How do you go to countries that are developing their economies and say, you should take a pathway that has more constraints than already developed economies took? There's a moral question there and all of that, and I won't attempt to address that. That's not my domain here. But I would say from a technical perspective, I would say if someone were asking me the question, why would a country with a resource not develop it based on arguments that there is a global impact related to increased greenhouse gas emissions? If I were that country, I guess one way I would want to look at it is I would say, well, okay, let's say that we develop this resource. And let's say that in doing that, we benefit in terms of energy production. There is a measurable negative impact on greenhouse gas emissions globally as a result of that. Is it possible that those increased greenhouse gas emissions can translate back to me in a negative economic way? Could products or services or trade relationships be adversely affected as a result of that? I would attempt to evaluate the impact, if possible, of that trade-off on the benefits I would get from the increased energy generation in order to try and make a more informed decision about whether it's prudent to develop the asset or to refrain.
If you have any more questions, please unmute yourself, ask REVIS. There is a question in the chat box. Andy Chung, would it be beneficial to reduce the importance of cost as a dominant driver of investment? If so, what are the ways to do so?
Well, I think it would be beneficial to reduce that importance, or the way I would phrase it is create more balance between the cost aspect and the other aspects of value the different assets deliver, so that you have a more balanced view of what you're getting if you choose to make an investment, whether you're a utility company or whether you're a government making policies to help a particular technology development. Obviously, our governments spend a lot of assets helping certain technologies deploy and develop over time. Renewables, nuclear, advanced nuclear power are examples. So yes, I think there would be a benefit in doing that. In creating more balance. I wouldn't advocate that cost is not important. I would simply say you need to balance it. Just a quick comment on cost. Having said all the things I've said about all the other aspects of value, cost is important because it's kind of a barrier to entry. I mean, if you don't address costs, then you're not going to attract investors. If you can't attract investors, you can't do anything else that you want to do. So one has to recognize that necessity. And I'll make another quick comment about the cost before I go to the question of how can you make that possible to create more balance. The other comment I want to make is that I remember several years ago when there was an expectation the United States was going to have a national greenhouse gas policy. That was in the early 2000s. That didn't eventuate, but at the time, a lot of studies were being done to evaluate the most cost-effective way to achieve that. And a study was done that looked at the benefits of introducing lots of greenhouse gas-free technologies, renewables, geothermal included, and so on. Unfortunately, that study had a little bit of a flaw in that it looked at it framed the question. This is going to the cost issue here for a second. That study framed the question: is it desirable to invest $1 in a geothermal plant or a wind farm as opposed to investing $1 in a coal plant or a natural gas-fired turbine? The question was framed within the boundary of power generation. In the reviews of that study that were done included, I think, a very cogent review by Bloomberg, which was a financial organization, who observed that when an investor looks at $1, the options they're considering for investment of that $1 go well beyond the power sector. Instead of investing $1 in geothermal or $1 in natural gas combined cycle, that investor can invest $1 in real estate or in some other industry, because the return on investment is higher there. So when looking at questions of cost, one has to recognize that cost has to remain a pretty important component, because investment decisions are going to be viewed in terms of, well, maybe I won't invest in a power asset at all in the first place. I'll invest in something completely different. So that's an important question to keep in mind. Having said that, I think the avenue to creating more balance in viewing cost is through this, through modeling of some sort. I've been talking about this energy economic modeling. Maybe there are some other choices, but I think we need to take these different variables that represent value, reliability, availability, operational flexibility, and so on. And we need to create a way in which a non-technical person who's a decision maker, a policymaker, or a regulator can see those variables and see what the impact is by increasing or decreasing the emphasis on one of those variables on the outcomes. If we are able to do that, we are going to give them an ability to see what the trade-offs are. You may not get the outcome you want or decision you want, but you will have a much better chance of getting a more balanced view.
Excellent. James has a question here. I was waiting for your recent comment on the importance of cost to be emphasized. Oops, what happened? Let me read that again. I was waiting for your recent comment on the importance of cost to be emphasized and competitive pressures for the investment of that monetary unit dollar. I guess, James, I'm sorry, is this a question or a comment?
I think it was a comment in order, from my perspective, to put balance to all of the pressures that have been raised in this presentation, which I can tell you 20 years in working in this, I have never heard anybody put such a cogent discussion of the whole scope of what this problem of electric power generation is. And I truly appreciate your efforts, sir. Thank you.
Thank you.
Thank you. Thank you, James. Well, here's another question in the chat box. What effect will the environmental laws and profitability of mining rare metals have on energy transition?
Well, that's sort of a two-part question, as I understand it. I mean, let me start with environmental laws. That's probably closer to what I'm knowledgeable about. I think basically, I'll take this question as an opportunity to frame a broader understanding, which is this. I think it's like driving your car. You get in your car to go to your family for the holidays. Now, if you're trying to optimize the cost of that trip, you might drive at an absolutely constant speed and on a certain route that would reduce road friction and all these other things in order to get the absolute lowest cost fuel cost. But you have other considerations. You would like to get there within a certain period of time. You would like to get there safely. You know, there are other considerations, which, so you may be willing to pay a higher cost in order to have those other priorities addressed. I view the environmental laws as that. These are priorities which are derivative not of efficiency goals, but a derivative of other concerns. And we wish to impose constraints on how we produce electricity in order to achieve them. And what we are saying as a society is we're willing to accept higher costs if necessary. Maybe that won't be necessary, but if necessary, to meet those things. So I would say, I as an engineer, as a technical person in the power industry, my view is I view those things as inputs to my problem. I'm told we must have no greenhouse gas emissions, and I have to figure out how do I achieve operational efficiency and reliability and safety within the framework of that constraint. That's how I view it. And if the output results in a higher cost or some other limitations on how we operate power plants or transmission lines as a result of that, then my goal is to make those as clearly understood as possible to policymakers and regulators in the general community, so they understand the implications of choosing to have those environmental laws. And if the choice is we're going to do that, then that's what we're going to do. As it relates to retrieval of rare earths and things like that, I'm not sure. I'm not quite sure I understand the connection, other than I'm sure there's energy involved and more environmental impact perhaps in doing that.
Well, I think he may be referring to rare earth elements, elements of battery storage.
Oh, I see. Okay. Oh, you
vehicles
mean,
and
in other words,
so on.
yes. Okay. Well, that actually, okay. Thanks for that interpretation, Ramesh. And assuming that is the interpretation, I think that actually can also be related to maybe even a broader question, which is, as we look at technology choices on generation or in transmission distribution, like for example, ceramic conductors and overhead transmission lines, for example, or even there's still been work being done on superconductor, high temperature superconductors, which hasn't been reached fruition yet, but you may, or another one, actually a better, more immediate example is solar panels. Right now, solar panels, the ones that you buy on the market, the ones that are going to get installed in your house, in your neighborhood, are, multi-layer, solar cells, which contain some not super exotic, but somewhat exotic materials that will eventually have to be disposed of. And so, just as in creating batteries and using these rare materials to create these batteries, and you have to recover those materials to do that, and that has an environmental impact and a cost. There's the other end of the spectrum, which is the refurbishment or recycling of batteries or solar panels or things which now have reached the end of life. For that matter, a wind turbine may not be indefinitely refurbishable. It may eventually have to be salvaged. So that is another interesting question, is to represent the energy cost and the environmental cost associated with the whole life cycle. That is a whole area of research that exists, as well established, this life cycle research looking at that question. I know EPRI does work on that area. I'm sure others are doing that too. So that's a very good question. What are the life cycle impacts of choosing these different technologies? And I think that is very important to look at that before choosing certain technologies.
Well, I think it's coming to that time when we need to close down. Revis, thank you for being so patient and answering
My pleasure.
a wide variety of questions. I mean, and thank you, audience. You brought up some very interesting questions. As I mentioned before, Revis will be back next semester to go into some details of a couple of seminars that we will be presenting. But meanwhile, Revis, thank you very much. And audience, we will have November 14th is our next seminar, and we have a speaker from Uruguay. Very interestingly, it's a country which has 93% clean energy. And if you caught a recent article in the New York Times, Uruguay is pointed out as an example of how a sustainable society ought to prioritize how they live, in fact. And it was a very interesting article. And we will have not only the presentation by the speaker from Uruguay, but we'll also have a half-hour discussion on what makes Uruguay so sustainable. So it'll be a little longer session, but hopefully a more enjoyable session. That's November 14th, when we'll have this seminar, energy systems engineering seminar. Anyway, thanks for your attention. Thank you, Revis, for your talk. And look forward to seeing you guys very soon.
Thanks for all the questions. Appreciate it.
Okay, bye-bye.